Take a look at this problem. It's a problem involving area of bounded regions. And the region, it is said that the vertical line x is equal to alpha. It divides the area of this region, and it's not explicitly mentioned that it is the area which is bounded by a function and the x-axis or something, but it's given in a way that y lies between x cube and x, and further the value of x lies in the interval 0 to 1. And now we need to find out the right options from the given 4. So let's have a look at this particular region first. If we are able to mark the region properly, then half of the problem is done. So what is happening is, so y is the region between x and x cube in the interval 0 to 1. Okay, so let this be 0, let this be 1. Now what is this function y is equal to x? Okay, it is nothing but the linear function. And then we have the cubic function x cube, which would be something of this form. Okay. Alright. Now what's being said is that the region that we are looking for consists of all those points whose y coordinate lies below x but above x cube. Or in other words, we want to find out the region which is shaded as follows. Okay. Alright. So once we have obtained the region R, now it is just a matter of using the property of integrals. So what does it say? It says that this line which is given by x is equal to alpha, so it may be some line of this form. Some line of this form. We don't know exactly what is the value of alpha. Okay. But what we know is that it is such a line so that the area is getting divided into equal parts. So which means we can very well write the equation that, so how can we write down the area in terms of the integral? It's very simple. It is nothing but the integral of the difference in the areas which is bounded by the function y is equal to x and y is equal to x cube. So it is x minus x cube. Okay, x minus x cube dx. Now what can one write? One can write that if you take the area from 0 to alpha of this curve, then it will be equal to half of the area which is bounded from 0 to 1 of the same curve, x minus x cube times dx. Okay, we have just made the use of the fact that this line is dividing it into two equal parts. So this area is half of this entire area. That's all. Alright, so now it's a simple thing to how to go about it. So we have, if you use the thing, we obtain this as alpha square by 2 minus alpha power 4 upon 4 is equal to 1 by 2 times. So let's see what is this. So this is x square by 2 minus x power 4 by 4. So, and if you put the limits, we get 1 by 2 minus 1 by 4. So this happens to be 1 by 2. So this is 1 by 8. Okay. So let's see what is the equation that we obtain. We obtain the equation as 2 times alpha power 4, okay, minus 4 times alpha square, and then we have plus 1 equal to 0. So let's see if it is matching them. Yes, it is definitely matching option A. Okay, so we have found out an equation which is being satisfied by this variable, the number alpha. Okay, nowhere is it asked us to find out exactly what is the value of alpha, but we need to find out is it lying between 0 and half, or is it lying between half and 1. Okay, so that essentially depends on how exactly this y is equal to x cube function it is going. So although geometrically it is not so easy to find out whether alpha lies on the left of half or right of half, but we can make use of some theorem, like for example the intermediate value property. So let us plug in the values of 0, half and 1 in this particular expression. Okay, so let's call this as, say, p of alpha. Okay, now if you put p of 0, then it's clear that the value is equal to 1. Alright. Now let's put P of half. P of half, if we put, then we get here. So this becomes 1 by 16. So that is 1 by 8 minus 1 plus 1. So it is equal to 1 by 8. Okay. So here you can clearly see that P of 0 and P of half both are positive, and hence we cannot make use of the intermediate value property. Now let's see what happens to P of 1. So if you put P of 1, then it's clear that this is 2. And then we have minus 4 here and we have plus 1 here. So it is equal to minus 1. So now you can make use of the intermediate value property, because we have obtained that if you plug in the value of x to be equal to half or alpha to be half, it was negative. It was positive, but when you put alpha equal to 1, it is negative. Which means, therefore, alpha, which it's alpha equal to, or rather P of alpha becomes equal to 0 when alpha lies in the interval half to 1. Okay, we are making use of the intermediate value property, and that is the option number D is also true. So as such, we cannot say anything about the 0 between 0 and half just by using the intermediate value property, because if the sign is not changing, it does not mean that there are no roots existing in that. But geometrically, we know that there is only one possibility, that either it lies between 0 and half, or it lies between half and 1. And we have showed already that it lies between half and 1, and thereby we have found out both the right options to this particular problem. So this was again a very good problem, because first of all, it was not explicitly mentioned that it is the area under the curve of a particular well-defined function, but rather you had to make out what is it, and then use basic integration to represent the area as the integral of, or rather the area under the curve bounded by the coordinate axis.